Web3 development used to mean manually typing out thousands of lines of boilerplate code. Now, you act as the system architect. You define the logic, constraints, and structural boundaries, while your AI collaborator generates the actual smart contracts. This poster details the Flare Summer Signal Hackathon Challenge to build the future of Web3. To meet that challenge, we will build a cross-chain smart contract on Flare that autonomously executes an action the moment it detects an XRPL payment. This diagram shows the exact pipeline we need. First, an XRPL payment is initiated. Second, the Flare data connector verifies that payment. Third, a Flare smart account wakes up. And finally, an AI agent evaluates the current data and executes a transaction. To start, you need 3 tools ready. Open up an AI coding environment like Cursor or Claude, install the Foundry Development Toolkit, and set up a local .env file configured with the Costin2 and XRPL RPC endpoints. Blockchain transactions are public and permanent. A minor syntax error can compromise an entire protocol. By positioning the AI as a structural collaborator, rather than a simple autocomplete, you build rigorous verification and adversarial testing into the code from the very first prompt. Standard AI models often hallucinate fake smart contract syntax when asked to write Web3 code. To fix this, we use the Model Context Protocol, or MCP, which connects the AI directly to Flare's live official developer documentation. Point your MCP configuration to the Flare Developer Hub endpoint. Then jump into your terminal and install the specific Flare AI skills: Flare General, Flare FDC, Flare FTSO, and Flare Smart Accounts. Your AI now understands Flare's native protocols. Step 1. Prompt your AI assistant to scaffold a new Foundry project using the official Flare Foundry starter template. The AI will automatically clone the repository and install the baseline dependencies. Before moving forward, pause and verify your .env file. Confirm that your private keys are correctly formatted and that your Costin2 and XRPL remote procedure call URLs are active. Next, specifically instruct the AI to open the foundry.toml file and set the EVM version to Cancun. This step is required because Cancun supports the advanced cryptographic operations needed for cross-chain data verification. By forcing the AI to pull directly from the Flare Developer Hub through the Model Context Protocol, the generated codebase relies on proven protocol mechanics rather than outdated or imagined smart contract structures. Now we build the logic. Prompt the AI to generate a Solidity contract that acts as a custom execution target, specifically for a Flare personal account. Tell it to accept calls only from the master account controller. This diagram illustrates the Flare data connector processing user requests via attestation providers. Instruct the AI to integrate this interface to verify XRP payments. Data flows from external chains into Flare, using decentralized consensus to validate events, eliminating centralized oracles. Next, tell the AI to import the FTSO v2 registry. We need the contract to fetch the real-time XRP to USD price feed. This ensures the smart account can calculate the exact value of the incoming tokens before executing its logic. When you explicitly prompt the AI to embed these data and price verifications directly into the architecture, the resulting application requires cryptographic proof to execute. It naturally rejects unverified data injections. With the contract structured, prompt the AI to write a TypeScript integration script. Specify that it must use the XRPL.js and Flare TX SDK libraries to reserve a minting tag and execute a transaction over on the XRP testnet. Now we move to simulation. Tell your AI to write an adversarial Foundry test. Instruct it to simulate an unauthorized user attempting to bypass the master account controller and execute functions directly. Run the command forge test in your terminal. Review the output. If the attacker successfully bypassed the check, or if the contract reverted unexpectedly, you will see the exact stack trace of the failure on your screen. When you hit an error, copy and feed that exact error trace back into the AI prompt. The AI will analyze the gas usage and state variables, identify the vulnerability, and generate the necessary code patch. Apply the patch and run forge test again. Once the terminal displays passing results across all edge cases, the code is solid. By deploying specialized AI models to actively try and break your code locally, you expose logic flaws and secure the protocol before a single line of bytecode is committed to the live network. To deploy, enter the forge script command into the terminal, append the broadcast flag, and point it to your Costin2 remote procedure call URL. Check the terminal output to confirm. You should see the newly generated contract addresses and the transaction hash proving the deployment was successful. This schematic details the implementation of a confidential, federated system. As your projects evolve, autonomous AI agents operating within trusted execution environments like this will be able to process sensitive off-chain data and orchestrate highly complex smart account operations securely. Now that your base cross-chain trigger is live, push the architecture further. Prompt the AI to expand the smart account logic to automatically route those incoming funds into DeFi yield vaults or to rebalance collateral based on live price feeds. The manual coding of basic functions is rapidly becoming obsolete. The builders succeeding in Web3 are operating as system architects, using AI to rapidly prototype, test, and deploy evidence-based, verifiable economic automation at scale.